just as with heat, there is a relationship between a quantity of work, called W, or using the symbol W, and a rate of work flow, W dot. We'll use a different analogy this time, and either analogy, the water flow out of a tank, or this analogy of velocity and position, either one works for both heat transfer rate versus heat and work flow rate versus work. Now the units of anything with a dot on it, like the Q dot or the W dot, that will always be energy per time, so something like watts or joules per second, which is the same thing, or maybe foot-pounds per second. Okay, all of those would be power, whereas W and Q both have the units of, or the dimension of energy, and therefore units like BTUs or joules or Newton meters or something like that. So let's go through this analogy and let's think through it with me. If you have, imagine a vehicle going along a road and it's moving from one position to another. So you see it begin at position 0 and it ends up at position X, okay, whatever that position is. How could you figure out how far that is? Well, if the vehicle is moving at constant velocity, you could just multiply the velocity times the amount of time that it takes for it to traverse that distance, and that would give you the position change, right? Now, if the velocity is changing throughout that whole move, well, then you have to integrate the velocity over time. But let's just take the simple example where the flow rate, basically the flow of position versus time, the velocity, is constant. Then say you're doing 50 miles an hour and you travel for a second, well then you've moved about 73 feet. You can see some conversion factors there to pull it all together. In the same way, work and power, or the rate of work flow, are related by an integral. Okay, so if you integrate power over time, you get work. Now if the rate of work is constant, if the power output of whatever it is, or input, is constant, then it's easy to calculate the amount of work flow during that time as simply the power flow rate times time, and that gives you work. So for example, if the power flow rate is 5 kilowatts and it flows for 10 seconds, then that's 50 kilojoules of energy, because a kilowatt is a kilojoule per second. The seconds cancel, we end up with kilojoules. Now, mechanical work is something that you've probably heard about for quite a while now. You've heard about work is equal to force times distance. Well, that's not exactly true, because if the force being applied to an object over time varies, then the amount of work actually has to be integrated by, or well, I'm sorry, the force has to be integrated over distance to come up with the total work. Imagine you're helping somebody move and you're sick and tired of picking up boxes and taking them out to the truck, so you decide to push one along carpet. Well, you're doing a decent amount of work. Now, if you push faster, does the force change? Well, it changes a little bit, but not much, but you're putting out more power because you're applying a force through a distance quicker, right? So the whole point here is that if you want to figure out how much work is done, you have to count up all the force times distance. And if the force is constant, then work is simply force times distance. Now, specific work is something that relates closer to this course, and you may not have thought of it yet. Imagine that you do a certain amount of work on a box that has a mass of, I don't know, let's say it's 100 pounds. That's why you didn't want to carry it, right? So if you do a certain amount of work on that box, if you divide the work you've done by the total mass of the box, you can figure out how much work was done per unit mass, okay? And that would be a specific work, and it's something that is important for us in the course. Now, let me hopefully help you understand this a little bit, because I know that you know work is force times distance, but I want to kind of bring it home to you and give you a real-life example. As usual, I'm trying to get into shape, right? So it's a little bit embarrassing. My father was a minor bodybuilder back in his 30s or so. I remember being a kid, and he'd take me and my sisters down to the Y, and he'd work out for several hours. Seemed like forever, you know. I don't know what all he did. I don't know what kind of, maybe he had a bunch of eggs he ate in the morning, but he actually built up fairly well. Part of it is he was shot in Vietnam, and he was trying to build up his muscles to compensate for that, and he did a fairly good job of it, really. As a matter of fact, he's in his 70s now, and his arms are still bigger than mine, so it's embarrassing, that my dad's this kind of buff guy, and I'm here this geek weakling, but that's okay. So I decided I'm going to put my knowledge to the test, right? I'm going to start trying to use what I know to build up my body as well. Hopefully, my real goal is to be, healthier. I know I'm not all that healthy right now. So I've always been able to do regular push-ups, okay? So I can get down on the ground, plank body. I could have pretty good form, feet on the ground, and do a push-up, but I could only crank out, I think, about 20 or so, consecutively. And so I decided I wanted to build up my ability, and I thought, well, the difficulty is in doing the next push-up, right? 20 is okay, but 21, I don't know if it's a psychological barrier, I don't know if I'm just too weak or what, but it's just, for a while, it was very difficult to get that last push-up in. So what I did is I decided, I've got a weight bench downstairs. I've got some weights. I think it's 50 pounds, something like that. Maybe it's 60 or 80. I don't remember now. So I thought, there's always this question I had, which was, to build up muscle, do you use high weight and low repetitions, or low weight and high repetitions? And some people I'd heard say, low weight, high reps will give you definition in your muscle where it's shaped nicely, whereas high weight, low reps gives you mass, right, so you can build up your body. And so I don't really know which one's true, and so I decided, I think maybe what really matters is the quantity of work done. In other words, work is force times distance. So if I've got the bar, right, to my chest, it doesn't matter if I'm doing a push-up or if I'm on my weight bench doing a bench press, it's basically the same motion. So I decided, I'm going to figure this out so I know how much weight there is on the bar. I wondered how much weight I was pushing down, so I just grabbed a bathroom scale and put my hands on it out straight in the push-up position and found out it was about 130 pounds. So if I do a whole stroke, I'm pushing 130 pounds about the displacement of my arm, and I have the same displacement on the weight bench, right? And so I thought, well, which way is going to build up muscle? I don't think it matters. I think that the amount of work that you do matters, the total amount. So now I need to not only multiply stroke distance by weight, but also by number of repetitions. Here's something kind of interesting. So I did that, right? I did as many push-ups as I could one day, counted how many there were, and then did as many reps on the bench press as I could with the weight I had. The product, since the stroke is the same, I took the distance out of the equation, but since the stroke was the same, all I needed to do was multiply the number of reps by the weight, and I got the same result, or pretty close to the same result. When I did push-ups at 130 pounds, I could do the product of whatever it was, 20 reps or so. Whereas in the whatever that product is, 20 times 130, I guess that would be what, 1,300, 2,600? Okay, so 2,600 pounds essentially that I've lifted, if you imagine pushing the weight and then letting it down and then pushing the weight again, letting it down. In the same way, the product of the weight and the number of reps on the weight bench was really close to the same thing. And so I think, I don't know that this is true, but my opinion at this point is that basically the energy you need to use when you're working out is already stored in the muscle, and that's why your muscles become fatigued. I know there's a lactic acid or something I've heard that's formed as well. I don't know biology. I don't know how that works very well. So I'm trying to work with what I do understand, which is energy and work and so forth. And it was just interesting to me to think, well, I'm doing these reps with lower weight, so the next repetition is actually easier with lower weight than if I was doing an actual push-up at 130 pounds. I mean, I can get another rep of 50 pounds, but another rep of 130 pounds doing a real push-up, that's difficult. And the funny thing is, I've gone from being able to do about 40, whatever the math was, I don't remember, maybe it was 45. I've gotten all the way up to 65 reps with 50 pounds, and so now I'll report back to you later if I can remember, but now I want to try some regular push-ups. That's the next experiment, and see if maybe I'm beyond that limit that I used to hit. So there's a little practical example for force times distance work, and if you see that I'm still not in shape next semester, you'll know either my theory is wrong or I got lazy, one of the two. Spring work is a little more difficult. Now with a spring, if you take a spring and you stretch it, you're doing work, you're applying force through a distance, but the force increases because we usually think of a spring as a linear spring. So since the force varies versus distance, we have to actually integrate that force over distance. If you do that, since you know the form of it, right, F equals kx, x is a displacement, ds is a displacement basically, or x technically is a position, ds is a displacement, but they're basically the same thing. So when we integrate over the variable, it would really be integrating over dx, if you want to think of it that way. You end up with an equation for how much work is required to move a spring from one position to another. Now these two positions, one thing I don't like about this equation is that really that x2 and x1 is the distance of the end of the spring from its rest position. So you have to set your x equals 0 coordinate at the rest position of the spring for this equation to make any sense. Electrical work is another form of work. So when you're having electricity flow in your laptop or your cell phone or whatever, that is a form of work. And the reason is that it's a generalized force through distance. If you think about electric potential, it's kind of like pressure or force, and it's pushing charges through resistance. So that is a generalized force and a generalized motion or generalized distance. Now in the electrical world, the calculation of energy is not really used all that much. Really, it's electrical work is equal to the electric potential times the number of charges pushed through a resistance. But that's not really what we usually talk about. We usually talk about electrical power. So electrical potential in volts multiplied by the current flow rate, because I is current, but it's not just current number of charges, it's current per time. So it's a flow rate of charges. Now, of course, in the electrical world, you can write this many different ways as I squared R or V squared over R, and you get the same result. But we're still talking about work, an amount of energy, and power, with the dot above it, work per time, even though it's electrical in nature. Now, heat and work are similar. Both are boundary phenomena, so they are not things that the system can possess. Okay? Systems can possess energy because energy is a property of the system, but they cannot possess work or heat. Work and heat are just energy in motion. Okay? So you got to understand that work and heat are associated with moving states from one to another. In other words, they're associated with processes. They're not associated with states. Both heat and work are what are called inexact differentials, and so we use this terminology, this odd Kronecker delta instead of a D. If you think about a property of a system, like volume, for example, if you change the volume of a system, it doesn't matter exactly what path you take. The change in volume between the two states will simply be the difference in volume. Now, at this point, it's probably best to bring in a little show and tell piece and hopefully explain this. So this is a little two-cycle engine. I'll try to keep it in view so you can see what's going on. Let's think about just the volume of the system. Okay, so I'm going to go from bottom dead center. Here's the volume of the system. The gas is above the piston. And I'm going to change it from state 1 to state 2. Okay, now if I measured the volume here and the volume initially, I could tell you the volume change. It's just the difference between those two. Let's do that experiment again. So here's state 1. Now I'm going to move to state 2, but in an odd way. Watch this. So I'm going to go up, back down, the other way around. I'm going to play with it. Fine, and finally there we are at state 2. Now the volume change is exactly as it was before because volume is a principle of the, or is a property of the system. You see, so the volume is just the difference in volume between state 1 and state 2, no matter how I get there. In other words, no matter what process path I take. But now let's consider work. I'm doing work because I'm rotating through a distance with a torque. Right now it's not much, I'm just overcoming friction, but that's what I'm doing here. So as I do this, as I rotate over and over, I'm going to go from state 1 to state 2, but by this path. Are you ready? So there's one path. I went from state 1 to state 2, but I can't take the difference in work between the two states because the system doesn't have work. The amount of work I had to do depends on the path I took, and the path I took was multiple rotations. Now let's do that again, but let's take a different path. Here we are. Which one had more work, the first one or the second? Well, obviously the first involved more work, right? Because I was playing around with it. I still ended up in the same final state, but the path I took was very different from the path I took in going directly from state 1 to state 2. And so I did more work in the first case where I was just playing around with it, right? I did a lot more work in that case than in the second case where I simply moved directly to the final position or the final state. So that's why work and heat are not exact differentials. Okay, so you can't say a change in work for a system. You have to say the work in going from state 1 to state 2 along some process path that may or may not be known. So the change in volume between these two states, state 1 and state 2 on the graph here, is the same. It's 3 cubic meters, but the work required is different because we're taking two different paths. Another way of saying this is that the area under the process curve is dependent on the shape of the process curve, and by the way, that area represents the amount of work done in moving between the two states. Another way to think of this, I guess when I made these slides it was back when the Wii was popular, so they're a little dated now, but It's pretty simple. Think about it. You got your whatever your dream console is. You just bring it home and you set it down on the table. You're about to go and get what you need in order to set it up and enjoy a few games. And you need to move it to the end of the table. Okay, so you have a couple of choices. You can slide it from position 1 to position 2 by path A, or you can slide it along path B. Now, the initial and final states are exactly the same, but the work associated with the longer path B is more than the work associated with path A. So you can't say the change in work of the system, because the system doesn't have work. It's the process that involves work. And obviously the amount of work required to move along the longer process path is greater for B than for A, right? So it's not much difference, obviously. We're just talking about friction. Friction is the force you're working against. But still, there's more work associated with path B than path A.